Good evening, ladies and gentlemen. Welcome to the Royal Society. Now, I am Uta Frith, and I'm absolutely delighted to introduce today's lecturer, Professor Hasok Chang. We will be recording this lecture, so just let me remind you briefly that you should turn your mobile phones off. And one other bit of reminding that just in case of emergency, the exit doors are on this side. Now, tonight's talk, entitled "Who Cares About the History of Science?" is being given by Professor Hasok Chang, the winner of the 2015 Royal Society Wilkins-Bernal-Medawar Prize. The Wilkins-Bernal-Medawar Prize is awarded to a scientist, historian, or philosopher who has demonstrated an exemplary contribution to the social function, the philosophy, and/or the history of science. And recent winners include Dr. Roger Highfield, Melvyn Bragg, Professor David Edgerton, Sean Eade, and Dr. Jeremy Butterfield. I believe that one or two of these people are actually here in the audience tonight. Professor Hasok Chang is Hans Rausing Professor of History and Philosophy of Science at the University of Cambridge. And I met him a long time ago at UCL when he was there for, he tells me, 15 years, in fact. Professor Chang served as president of the British Society for the History of Science from 2012 to 2014. He is a co-founder of the Society for Philosophy of Science in Practice, and he's a founding member of the Committee for Integrated History and Philosophy of Science. Ladies and gentlemen, I'm pleased to present Professor Chang.
Thank you so much. Thank you very much for the kind introduction, Professor Frith. I'm sorry about that. And it's a great honor to present this prize lecture. I'd like to thank the Royal Society and everyone involved in the organization of this event, and all of you for being here, including the previous prize winners. Now, I've chosen a provocative title for this lecture, but it is not a rhetorical question or simply intended for attracting attention. It is a serious literal question that I have been facing every day for over 20 years in my work as a practitioner and a teacher of the history of science. And in recent years in my work for the British Society for the History of Science and other similar organizations as well. Now, from members of the public, from educators, from practicing scientists, we often get very skeptical questions about the use of the history of science. The situation is similar for our sister discipline, the philosophy of science, which I also practice. The great physicist Richard Feynman is said to have quipped that the philosophy of science was only as useful to scientists as ornithology is to birds. I fear what he might have thought about the history of science, which would be more like paleontology, obsessing about extinct birds. In a progressive enterprise like science, why does one need history? Why worry about the past of science, which might be considered at best an inferior approximation of the present, and at worst a set of dead ends that our ancestors thankfully managed to escape from? We can get some insight into this by reminding ourselves what history of science does get mentioned in science textbooks or the popular media. they tend to appear as mere garnishes to presentations of serious scientific content. Stories of heroic scientists who overcame adversity, tragic scientists hampered by human limitations and circumstances, fortunate ones who made great discoveries by exploiting chance happenings, strange ones who engaged in bizarre experiments or devised fantastical theories, etc. Many of these stories are myths, even if they're not as crude as the iconic tale of how Newton discovered the universal law of gravitation thanks to an apple that fell on his head, which we all know about. Actually, there's a better story, which goes that gravity was discovered actually by a Southeast Asian long before Newton, who was lying under a durian tree. Except he didn't live to tell the story to anybody. I assume you've all heard historians of science groaning or fulminating when presented with such stories, not that one, but the other ones, or you have made such noises yourselves. But in the rightful condemnation of such myths, there is something important that is often missed out, namely the question of purpose. What exactly is it that we should be trying to achieve by writing and teaching history? The heroic tales or the bizarre anecdotes found in popular historical accounts do have positive functions in the right circumstances. They can give inspiration to students aspiring to enter science or excite people's curiosity about the process of science. So they may serve as a hook into more serious scientific endeavors. I take it that was the main point of Dr. Highfield's lecture in 2012. When we clear away the mythology, we need to ask what we are putting in place instead and to what purpose. We must ask ourselves not only what good history is, but what good history is. I'm not disputing that we historians of science should take pains to show that stories like the apple falling on Newton's head have no firm historical evidence. We should. And we should remind people that the idea of gravitation had a long and complex gestation in the thinking of Newton himself and many of his predecessors and contemporaries. That Newton's true achievement was not thinking up the idea of gravity, but formulating it in precise mathematical form and applying it to important celestial and terrestrial phenomena. That his thinking in physics was intimately linked with his work in alchemy and theology, etc., etc. But we also need to ask what benefits will follow when people understand all of that. 30 years ago, John Heilbronn, very honored to have you here, who was the Wilkins lecturer before the three prizes were merged, Heilbronn urged his fellow historians of science to pay more serious attention to what he called applied history of science, focusing on its uses for general education, science education, and science policy. We historians need to see beyond our intense desire to understand the past correctly. For today, I'm going to set aside the problem of whether there is really such a thing as the unvarnished truth about history, not to mention the unique best interpretation of it. What I want to emphasize today is that in our condemnation of careless distortions of history, we often fall into another trap. This misstep begins with the faultless observation that many of the errors we want to combat arise from trying to fit the past into the framework defined by our present assumptions and concerns. In the words of Herbert Butterfield, the study of the past with one eye, so to speak, upon the present is the source of all sins and sophistries in history, starting with the simplest of them, the anachronism. His advice was that real historical understanding was achieved by attempting to see life with the eyes of another century than our own. That's in a way indisputable, but if we followed Butterfield this far, we might just have fallen into the trap that I'm referring to. We must not forget the fact that we historians are inevitably stuck in the present. no matter how much we might kick and scream about it. Even though history is about the past, history writing is for the living in the present. In our attempt to avoid the ills of presentism, historians often decline to think about our own present and fall into the illusion of selfless objectivity. But we cannot be clear about our own purposes if we do not consider our own present situation. Understanding the past is good, but the point of that understanding must be in the present. We need to articulate in which ways the misunderstanding of the past harms us and the better understanding of the past helps us. This is what I want to focus on in the remainder of today's lecture. In the phrase of the radical American educationist Neil Postman, we should ask how the past can improve our future. Now, let me start into that by taking a quick systematic overview of what the possible functions of the history of science might be. I would start by drawing a distinction between what is internal to science itself and what is external to it. Now, I know professional historians of science do not like this internal-external distinction today. It's not essential to my purposes, it's merely convenient. And I use it roughly in the sense defined by Dudley Shapiro, so you can go and review his work if that's of interest to you. But let me just get back to the scheme here. These days, the external tends to be emphasized more, with the current trend within the history of science field being on understanding science as a social and cultural phenomenon, and the obsession outside academia being about science as a driver of technological and economic development rather than something worth doing for its own sake. So we hope that a better understanding of the history of science will help us use and control science more wisely and support it more effectively in economic and institutional terms. But in the spirit of paying attention to what is neglected, I will focus my attention on the internal functions. Roughly speaking, that means asking whether the study of the past of science can help us improve present scientific knowledge. This is generally not at the forefront of historians' thinking, though there has been a venerable tradition of attempt to use the history of science to improve science education. There are many ways in which the knowledge of the history of science may enhance scientific knowledge itself. To conceptualize this more precisely, under the internal functions of the history of science, I want to distinguish between the orthodox and the complementary functions, as I call them. On the orthodox side of this divide, historical knowledge can help us understand better the scientific knowledge that we accept at present. This may actually confuse the beginners to know too much history, but to those who can handle some complexity, knowing how we came to know what we know can add a layer of depth to scientific knowledge, with a more nuanced understanding of concepts and a more assured justification of the results that we might otherwise be condemned to accept simply as gospel truth. Much of my own historical research has been in this direction, including what is in my two monographs, tackling very, very simple questions in science. History can also teach us about the scientific method. Again, something that historians of science these days prefer not to discuss, but I think we need to do it. Peter Medawar, one of the three greats whom we are celebrating today, thought that this was an area in which routine scientific training was woefully inadequate. He once wrote, "Ask a scientist what he conceives the scientific method to be, and he will adopt an expression that is at once solemn and shifty-eyed. Solemn because he feels he ought to declare an opinion. Shifty-eyed because he is wondering how to conceal the fact that he has no opinion to declare." If we think science is working well, we must keep it working well. So it's necessary that scientists are trained in the methods of science. This does, of course, happen for the specialist by way of learning by doing, but that is not sufficient. First of all, taking a historical viewpoint can be useful, rather than always being immersed in one's own narrow specialism. And for non-specialists, it is very useful to be able to learn about scientific methods by going back to the history when science was a bit simpler, without having to master the formidable technical details of contemporary science. And this links to the external functions as well, since people with no understanding of the scientific method could not possibly direct science policy sensibly. So I hope you'll take everything I've been saying so far as somewhat obvious, as useful reminders of what you already knew. In the rest of the lecture, I would like to focus on more unusual and controversial points by addressing what I call the complementary function of history of science, which is to generate scientific knowledge where science itself fails to do so. Now that sounds crazy, I know. So I'm going to try to convince you that this is actually a sensible thing to try. And it is in line with my more general notion of history and philosophy of science as complementary science. Now, the boundary between the orthodox and the contemporary is in the long run movable and permeable, although it often feels like a brick wall if you happen to run up against it. Now, there are three kinds of functions which I distinguish under the complementary. The first is that I find history is one of the best critical tools for the philosopher, and learning history is a wonderful way of opening one's mind to new possibilities. This works in two different ways. The Italian historian and philosopher Benedetto Croce once said, "Only historical judgment liberates the spirit from the pressure of the past." Learning how scientists came to believe today's orthodoxy can aid our understanding of present science, as I mentioned earlier, but it may also reveal that what we take as evident and necessary truths today were actually results of past decisions that were contingent and could have gone in a different way. This is the liberation that Croce is talking about. An excellent illustration of this function of history is given in the work of James Cushing, who showed that the establishment of the Copenhagen interpretation of quantum mechanics as orthodoxy was due to various historical contingencies, including the order in which some key events happened to happen. John Heilbronn had already detailed 10 years previously one key aspect of that history, namely the fact that there happened to be a group of physicists around Niels Bohr who actively set out to persuade everyone else to their new world view, whom he called the earliest missionaries of the Copenhagen spirit. It is significant that I learned the Croce quotation from Thomas Kuhn's Introduction to the Archive for the History of Quantum Physics. Now, against the consolidation of the Copenhagen orthodoxy, even Einstein's concern had little force. Now, one could argue that Einstein only made philosophical complaints without putting forward any alternative quantum physics. But as Cushing shows, when David Bohm did exactly that, putting up a new quantum physics, he was still sidelined and ignored. And here I'm not speaking as an adoring fan of Einstein, which I have been in my life. The absolute dominance of Einstein's own theories of relativity was itself a highly contingent event, and it would have been perfectly rational to maintain the ether-based theories of Maxwell, Kelvin, Lorentz, Poincaré, and other great physicists. Now, in addition to teaching us about the contingency of the present, the study of the past also serves to expand our conceptual horizons more specifically. We say truth is stranger than fiction, and actual past science can go beyond our imagination, because our imagination is usually heavily constrained by our present situations. and there were some quite loopy past scientists. The motto here is provided by the novelist L.P. Hartley, who opened his The Go-Between thus: "The past is a foreign country. They do things differently there." Learning history is broadening like traveling is meant to be broadening. It is a common occurrence for those of us who delve into old scientific texts to slap our knees and exclaim, "Yes, one could think like that," although it had never occurred to me before. Let me give you a couple of very quick examples. William Herschel, we say, discovered infrared radiation in sunlight in the year 1800. In fact, he didn't think that's what he had discovered. He thought he had managed to separate the rays of light from the rays of caloric, the substance of heat, using his prism, by throwing the rays of caloric off beyond the red end of the spectrum. It was very common during this time and beyond to think of caloric, the substance of heat, as something that could fly around at extremely high speeds, which is what they meant by being radiated. And there are very intriguing experiments like this one performed by Pictet in Geneva, where you put a warm object into the focus of this pair of concave mirrors, and at the other focus, a thermometer introduced in that place would immediately rise when the warm thing was introduced at the other side. And then they did the same experiment with cold. Something like an ice cube introduced at this one focus would immediately lower the reading of the thermometer at the other focus. And many people thought, well, cold, rays of cold were being radiated and reflected and focused. And one of the great advocates of this view was the great Count Rumford, the founder of the Royal Institution. Now, in addition to serving the role of opening our minds, past systems of science are valuable in themselves, I would argue. This brings us to the function of history that constitutes the recovery of lost scientific knowledge. Kuhn famously argued that when a scientific revolution happens, some knowledge that had been established in the old paradigm is liable to become lost. He accepted the so-called Kuhn loss as part of the normal course of scientific development. But I think there's no reason why historians should not contemplate with real appreciation what we dig up from the past. If the chemistry of phlogiston and Lavoisier's chemistry of oxygen and caloric once gave valid understanding of nature to the practitioners of those systems, then they can still provide the same understanding concerning the domains of phenomena in which they remain valid. This is how orthodox scientists actually treat venerable old theories of physics, such as geometric optics and Newtonian mechanics, which they still teach to every single student of physics. That same appreciative attitude could be extended with benefit to some of the theories that orthodox science has now rejected. Now, this agenda of recovery may be quite difficult to accept when it comes to theories. It is difficult to go against the confidence of current specialists, Nobel laureates, and so on, that the old theories were rejected for good reasons and they deserve to be forgotten. This is why experimental work is so valuable in this context, because our own judgment can more easily be independent when we come face to face with phenomena themselves. Let me illustrate this point with a few examples. The experiments which apparently showed the radiation and reflection of cold, the basic one was actually replicated by two perfectly sane American physicists, James Evans and Brian Popp. Their paper was published in the American Journal of Physics. As of the last time I looked at it, it had never been cited, except by me in my historical paper on this subject. Many historians of science have noted that the Romantic literary giant Goethe had an intriguing theory of light and colors, which he set up against Newton's optics. More lately, some historians and philosophers of science have taken the additional step of reproducing some of Goethe's numerous optical experiments. This is a fascinating line of work. My own experience at first with replication of such forgotten experiments was in the summer of 2004 at UCL, which I spent boiling water with utter fascination, in which I confirmed many implausible sounding 18th and 19th century claims that there were great variations in the boiling temperature and behavior of pure distilled water under normal atmospheric pressure, depending on the material of the vessel in which the boiling happened, on the rate at which the heating was done, and on the amount of dissolved gases in the water. Now, I'm going to refrain from showing you all of my beloved video clips of boiling water, as I see there are many people in the audience who have already seen them. Some of you more than once. Details can be seen on my online paper on the subject, whose address is at the bottom of the screen. Of course, as you've noticed, I couldn't resist having one of the clips playing in the background. The boiling in this innocent long-necked flask has by now reached the puffing stage, as it was called, in which only very occasional and very large bubbles come up explosively, while the temperature goes well beyond 100 degrees centigrade. You'll see in a moment that this one, in this very quiet state with occasional bubbles, is maintaining a temperature of about 104 degrees centigrade. Now, historical boiling was a truly formative experience for me, which greatly heightened my sensitivity to lost phenomena from past science. The next case I met with was this one, as I started looking into the intriguing early history of electrochemistry. Now, I should take this moment to thank my wonderful chemist colleagues who let me play around in their labs. Andrea Sella, Darren Caruana, Rosie Coates at UCL, and Peter Waters at Cambridge. So this is William Hyde Wollaston, London-based chemist, brother of the Cambridge professor of chemistry at the time. Now, he published in the Phil Trans of the Royal Society in 1801 this curious paper in which he tells you, if a piece of zinc and a piece of silver have each one extremity immersed in the same vessel containing sulfuric or muriatic, meaning hydrochloric, acid diluted with a large quantity of water, the zinc is dissolved and yields hydrogen gas by decomposition of the water. The silver, not being acted upon by the acid, has no power of decomposing water. But whenever the zinc and silver are made to touch, hydrogen gas is also formed at the surface of the silver. And then it tells you can use any other metal instead of zinc that will dissolve in the acid, and also the other side can be any metal which the acid doesn't dissolve. So silver being a bit expensive, I used copper. And here is Wollaston's experiment as reproduced by myself. So zinc wire goes in, this is hydrochloric acid. It dissolves while releasing bubbles of hydrogen. Copper wire goes in, nothing at all happens. This is all what we expect. And then Wollaston's beautiful little experiment simply consists in touching those two wires, upon which immediately the bubbles, sorry about the clumsiness there, bubbles start coming up from the copper wire copper wire as well. The copper is not dissolving at all. It's just somehow generating bubbles. In case you're thoroughly bewildered by what's going on here, I should explain that Wollaston put forward this experiment in the context of the excited debate about the operation of Volta's battery, which had been publicized just a year before. The topology of Wollaston's experiment is the same as the voltaic cell, namely two different metals with an electrolyte between them. In Wollaston's own view, this passage explains his view. I'm going to paraphrase it in slightly more modern terms. In his view, his experiment demonstrated that the chemical reaction between the zinc and the acid released what he called the electrical fluid, and the silver or copper, which did not react with the acid, simply conducted an overflow of the electrical fluid, passing it into the liquid. Wollaston thought that the action of electricity decomposed the water in the acid, releasing hydrogen bubbles, and the oxygen goes and oxidizes the metal. Translated into modern terms, Wollaston's explanation is that electrons are let loose from the reaction between the zinc and the acid, and that some of them are conducted over to the copper wire. As they come out into the solution from the copper, the electrons combine with the hydrogen ions waiting there in the acid and create hydrogen gas. Reproducing this experiment led me to many interesting questions and follow-up experiments, which I will try to tell you about shortly. But before that, there's one other simple experiment I must show you. And this comes from someone called Charles Sylvester. You've never heard of him, I'm guessing. I hadn't heard of him until I came across, rather by accident, this little paper published in Nicholson's journal in 1806. And this is an experiment described in one sentence. Right? If a thin coat of a solution of nitrate of silver be laid upon a piece of plain glass, and in the center of this be laid a bit of zinc wire, in a little time, a beautiful tree of silver will appear as if growing from the wire. That's it. And you read that and you say, oh yeah, sure. So I had to try it. How hard can this be? It's not very hard. I adapted it slightly, putting the silver nitrate solution into a thin plastic envelope instead of putting it on a piece of glass. So this is how it goes. First, immediately when you put the copper in, it gets covered in silver. It's because the nitrate likes to combine with the copper more than it likes to combine with the silver. I'm talking like an early modern person, but that's the easiest way to explain it. And it's a replacement reaction. Alchemists knew about this. No surprise there. The surprise is that it kept growing, silver on silver, into this beautiful set of patterns. And yes, just like Sylvester said, a beautiful tree of silver sprouted up in about an hour and a half. It's a fascinating thing to watch because you can actually see the fine needles of silver grow if you're patiently sitting there. Now, such phenomena recovered from the dusty depositories of past science deserve to be remembered and appreciated. They may seem trivial, but that judgment is most likely shaped by present orthodoxy. And the seemingly trivial phenomenon, like Alexander Fleming's Petri dish, can stimulate much larger developments. About the recovery of valuable things from the past, there are some beautiful statements I have from past historians. I'm just going to read to you the shorter one by the German historian of Rome, Barthold Niebuhr, who said, "He who calls what has vanished back into being enjoys a bliss like that of creating." And that quite sums up the kind of experience that I've had. Other historians who have been engaged in these reproductions of old experiments have also expressed. Now I'd like to address the function of the history of science that I call extension, meaning the extension of the neglected knowledge that we recover from the past. Now, almost every recovered experiment leads to open questions, which one can attempt to investigate by further experiments. That, after all, is the nature of experimental science. You do one experiment, it doesn't end there. It stimulates other experiments. So, having replicated Sylvester's beautiful experiment, I was naturally led to a question as to how it happens. Why doesn't the reaction just stop there, right? After all of the copper is covered in silver, why does silver keep growing on silver? This is worth thinking about. I don't know the answer yet. What exactly is the role of the inert metal, copper in my case, looking back at Wollaston's experiment. For Wollaston himself, it was just receiving an overflow of electricity produced by the chemical reaction on the zinc side. For Volta, who was arguing against Wollaston and his colleagues, the bimetallic contact was actually what caused the flow of electricity. So here I made a very simple variation in Wollaston's experiment, replacing the copper wire with a gold wire. Now here you can clearly see that the result is the same kind of thing, but very different. So zinc just going in. Very excited bubbles from the gold wire, and there's hardly anything coming out from the zinc. Yet the electricity, well, is it all being produced at the zinc? I believe it is, but what I think this little experiment shows, if I may put it in a modern paraphrase of Volta, is that the gold is clearly more effective than copper was in pulling electrons over from the zinc side. Chemists don't usually talk about this when they discuss electrochemistry. The physicists might freely grant, yes, there's contact potential, what's the big deal? But they don't talk about how batteries work, so we're kind of falling between the stools here. Looking at Volta's work revealed another important source of questions to me. Instead of acids, as in this experiment, Volta had used salt water in his original battery. I was intrigued by the electrochemistry of salt or sodium chloride solution, especially where the electrons would go when they're released into it. Because in the acid solution, the electrons, we say, combine with the protons or H plus hydrogen ions floating around, make neutral hydrogen, but there aren't enough hydrogen ions in NaCl solution. So where do the electrons go? Where are they received? Trying to make the effect easy to see, I decided to do a new experiment in which I pumped a lot of electrons into a saturated salt solution by connecting a little battery into electrodes inserted into saturated salt solution. So there's the solution, 2 copper wires connected to this battery. And let's see what happens. The moment the battery is connected, a prodigious amount of hydrogen gas issues from the negative electrode, as you can see there. That was an interesting puzzle, as there aren't enough H plus ions in a solution of NaCl to receive that many electrons. The only conclusion I could reach was that the influx of electrons results in a direct breakdown of H2O molecules at the electrode. Some scientists I've spoken to about this are quite skeptical about this idea, and others think it's so obvious that it doesn't need even discussion. So between the two, I lose. Meanwhile, the copper electrode on the positive side dissolves, creating that orange muck that you see, and that's the aftermath. There's a lot of that orange precipitate as well as a little bit of blue. Now, rather than plunging you further into the strangely intricate world of basic electrochemistry, starting with the question of what on earth is that orange gunk, I want to finish by showing you a different experiment. So if you wanted to see all of this, I'm sorry about that. I can come back to it in the questions if you want. Fascinating as the dissolution of the copper electrode was in the previous experiment, I didn't actually want it to happen because it complicated the question that I started out with, namely what electrons did when they went into the sodium chloride solution. So I thought I wanted to use chemically inert electrodes to cut out the confusing collateral damage going on. So there are various options, such as gold and platinum and graphite. To cut a long story short, I ended up doing this experiment using a graphite electrode on the negative side and a gold electrode on the positive side. So that's the setup. Up to 2 volts, nothing happens. At 2.2 volts, something begins to happen. On the minus side, you start getting bubbles. So that means if you know any electrochemistry of these circuits, something must be going on that side as well. But what could it be? At 3 volts, you begin to get suspicious indications. And I'll show you what happens at 3 volts. Is that gold electrode just dissolving away in the salt water at 3 volts. And at 3.5 volts, it's even more excited. At 4.2, it stops doing that. Now it starts producing a gas, which to me smells like the swimming pool, which means most likely we're producing chlorine gas and you must stop that experiment. Dissolving gold in salt water with 2 batteries was certainly not what I had set out to do when I innocently stepped into the history of early electrochemistry. And there's a story of failed gold plating as well, but I don't have time for that. At this point, many of you will be questioning whether I'm still doing history. Isn't all this just science and of a strange and weird and elementary kind? Now that's okay for me, and it's also perfectly sensible, I think, that not all functions of history serve the purpose of history itself. These questions, however, are in the realm of history and philosophy of science because today's specialist scientists don't deal with them. That again reflects the sense of what I call complementary science. Let me begin to finish. I hope that I've done enough to illustrate to you the possibility that the history of science may serve the internal function of improving scientific knowledge itself, especially by playing a complementary role of recovering and extending what orthodox science loses track of. I now want to take in the whole picture again as a brief coda to this presentation in 2 parts. The external functions of the history of science, which I have not spoken much about today, have a close parallel to its internal functions. If we think that science is a force for the good in society, learning the history of what has enabled it to be such will help us maintain its institutions and keep its social and economic benefits flowing. On the other hand, if we think that science is not being supported properly or that it is developing in such a way as to have harmful social effects in its applications or cultural resonances, learning the history of science will provide the critical awareness, recovery, and extension that we need in order to help set things right. For those who don't really acknowledge the internal-external distinction, the parallel I'm pointing out will be seen really as a continuum, and that's fine by me as well. I find great inspiration in the words of historian Paul Forman, who exhorted historians of science to embrace the obligation to decide for ourselves what is the good of science, and by our historical research and writing to advance that good, and to lose our intellectual subservience to the sciences. Such an active political conception of the history of science was also very important to J.D. Bernal, another one of the greats that we are celebrating today. It is also evident in the work of previous Wilkins-Bernal-Medawar lecturer David Edgerton. Another parallel I must note is between the functions of the history of science and the functions of other kinds of history. Here it is even clearer that the parallel must really be a continuum. Since science is undeniably a part of human society and culture, it makes sense that the history of science should be on the whole like the history of any other aspect of human life. After all, some of my inspirations, such as Croce, Marou, and Niebuhr, were not historians of science at all. The particular importance of this continuity is that in doing the history of science, we should not shrink from addressing the present relevance of the past, whether it be intellectual or social. I would like to close by returning to one of my starting points. I noted that history is often used in order to excite curiosity and give inspiration for science, and that this motivation often encourages distortions and oversimplifications of history. I hope that my remarks today go some way towards convincing you that curiosity and inspiration are not incompatible with doing full justice to history. Thank you very much.
I never knew that the history of science could be such fun and that you could get to do experiments rather than just look at the archives, at the journals. But
that's also fun.
It's also fun, I agree. So Professor Chang has agreed to take some questions from you, and we have people with microphones who will come to you when you raise your hand. So, yes, there's a lady with the green jacket.
Okay, so I was just wondering about the problem of past data in confirming, say, climate models. Past data being an instance of history.
Mm-hmm. Yes, that's a very important question. It's slightly different from the sort of thing I was talking about today, but I think it is an important point that useful ideas were being advanced, useful phenomena were being studied, useful data were being collected by the past scientists, and it is difficult but possible to gain information that's pertinent to today's science from such old papers. We in fact, had a master's student at Cambridge a few years ago who tried to do precisely that, and the result was very, very interesting to witness. Thank you.
Hi, Tom McLeish.
Yes, thanks very much. That was a wonderful lecture. We much enjoyed that. I wonder if the complementary aspect of that you spent most time on, you could tell me whether you think that in terms of current practice of science, in the context of Peter Medawar's quote you gave us right at the beginning, can help in the generation of hypotheses. You know, I mean, early in my scientific career, I was a very good boy, and I read Karl Popper, and I read all the, I read all the logic and refutations, and all the scientific method stuff, and it dawned on me that although all this stuff told us what to do with our hypotheses when we had them,
yes,
that's only half the business of science, and arguably less than half. No one I could ever read would tell me where to get the hypotheses in the first place. And I'd still like to know the answer to that question, but I wonder whether the study of history of science, particularly the recovery of some of these interesting nooks and crannies, is a place where we might generate better ideas than we might if we just stuck with our noses to our test tubes as they are at present.
Yes, thank you. I certainly agree that looking at some of the neglected past can be a wonderfully stimulating thing, precisely because those bits are neglected, which means that they're not quite consonant with how we currently think. So that's the particular use of the complementary aspect of the history rather than the orthodox. And I think you have raised a huge question for philosophy of science, right? Because philosophers following in the footsteps of Karl Popper often have said, yes, what we call the context of discovery is not our business because it is not amenable to logic. And I'm currently trying to dig up some other parts of the history of the philosophy of science which provide some useful ideas. And for example, I'm looking at the American pragmatists who had much more interesting ideas about how ideas are generated. And one of the things I've realized in doing my historical work is the importance of looking at one bit of knowledge to think what that implies about other things. So one experiment leading to others, and One very important thought process in that whole practice is what Charles Sanders Peirce called abduction. Right, you find a puzzling phenomenon and you just do your best to try to explain that phenomenon, and in that process you have to generate certain hypotheses, right? So I think that's an important kind of thought process that we need to pay more attention to. Thank you.
Yes, here's a question.
Thank you very much for the talk, Professor Verst. And I'm a philosophy student myself, and my question and the whole motivation of my question might be slightly geared towards a philosophy of science, maybe. So, for example, these days, like science, particularly in neuroscience, there are lots of findings discovered, like explaining away all about human like free will and determinism, that kind of thing. I know that might be not of your research interest or whatever, but then like that kind of findings actually tells a lot about the falsity might be a big word, but the incorrectness of the like philosophy, like moral philosophy or anything. But then I just want to, or maybe like in a way, it might sort of alter the public intuition we have on our confidence of free will and etc. But then I just want to ask you, as a historian of science, how you I mean, there's a lot of possibility with like from that, like there are lots of possibility of this scientific finding sort of changing the whole research programs in philosophy. So I just want to know what sort of like the role like history of science can have on this kind of issue, or maybe I don't know what sort of, you're also a philosopher of science anyway, so how actually can react to this? So.
Yes, thank you. I'm not sure how directly I can answer that question, but here's a very pertinent thing, I think. History, one of the things that history of science and history of philosophy teaches us is that that boundary between science and philosophy has been very fluid and very movable, right? So when you're thinking about things like history of mind now being heavily, I don't know, encroached upon by neuroscience, we need to think carefully about the boundary between science and philosophy, because there are some plausible arguments that philosophical questions may not be amenable to scientific answers, and vice versa maybe. I don't happen to quite believe that very strictly. In my view, I think philosophy has been inevitably in the passive position as the sciences make great progress and very often carve themselves out into specialisms. What's left is the philosophy, right? It's the wastebasket these days, what we philosophers are left to deal with, right? There was a time when Plato and Aristotle dealt with every intellectual question, and that was all philosophy. But then mathematics leaves, astronomy leaves, physics, biology, chemistry. Now what have we got? All the questions that we can't answer, right? That's philosophy, but I think that's important. That's why we need philosophy. And we need to be continually, I think, examining that boundary between what counts as science and what still remains philosophy. And we might take some of those questions back. There has to be a productive interaction, I think. Sorry, that's a long answer.
Very interesting answer, I have to say. So, yes, the gentleman who's just on this side. But there were some other hands up.
Well, to pursue that last issue on the demarcation criterion, your claim is that history of science, studying it, can increase our scientific knowledge, which of course raises the question, what is scientific knowledge? Precisely the demarcation question. I'm just wondering if you are using any criterion when you're making that claim. There is, of course, amongst many other things, the additional claim from Huygens and Leibniz, Duhem, Lakatos, that scientific knowledge is that which predicts novel facts successfully. you, I understand, reject that, but I just wondered what your criterion is when you're, to verify your claim that the history of science, study of it, can produce scientific knowledge.
Thank you. Sorry about that. I'm sure I'm not using a demarcation criterion specific enough to please you. I'm taking science, in one sense, completely broadly, as any kind of study of nature. In another sense, I'm taking it very narrowly, but not philosophically, right? So when I distinguish the orthodox and the complementary part of science, if you want, what is orthodox is determined by the scientists themselves. There's nothing we can do about that, right? Because whatever we say as philosophers or even historians, the scientists are not going to listen to that. But I think we have an obligation to accept that boundary, yet ask, is there anything valuable being left out from the scientist definition of what counts as science? Now, after having done that, I think we can apply other criteria, like the Lakatosian criterion of novel predictions. We might be able to say, look, here's a realm of investigation of nature in which people are making fantastic novel predictions. Why aren't the card-carrying scientists including that as science? I think we can engage in that sort of discussion, and that's very much worth doing. Yeah, that just wasn't the focus of my presentation today. Thank you.
So you're next.
Thank you, Professor, for your talk. So my question starts with this observation that today is tomorrow's history.
Yeah.
How should we, and by we I mean historians of science and scientists alike, then think about our current activities as they will shape the future history of science, and what perspective the future will have back on us? Does that carry any responsibilities, or should we just ignore it totally, pretend that the future won't really look back on us and carry on forward regardless? Do you have any thoughts on that?
I'm sure I can't give a good answer to that question, but a couple of notes, right? There's something that we philosophers of science love to talk about, the pessimistic induction from the history of science. Some of you know this very well, right? The thought that when you observe the long history of science, most of the theories that scientists used to love and accept as true have now been discarded. So if you do a simple induction on that, well, chances are 50 years hence, 500 years hence, most of what we believe now will be discarded by our more advanced future scientists. They're going to be really laughing at us for things like dark matter, but let's set that aside. So that's one thought. What does that imply, right? I mean, philosophers use that pessimistic induction argument to agonize about the realism debate, but I think it's more interesting to look at it from your perspective, right? What does that imply about how we ought to do today's science so that possibly it may not get laughed at and rejected by future scientists? And I don't think there's a simple answer to that, but I think it is worth considering, right? Why do scientific theories that are the flavor of the month for a time get later rejected? Sometimes it's because new data come up, but that's not usually why this happens, I think. So I think we need to recognize the trendiness, the fashionable things that go on in scientific theories. We need to guard against those. I think we also need to acknowledge that theories and methods that work in certain domains are probably likely to still work even well into the future, right? As long as we're still looking at the same phenomena. So it would be hasty to reject those just because the flavor of the next month comes up. And I mean, in my own extended view, this develops into a whole doctrine of scientific pluralism, but I'm not going to enter into that right now. Thank you.
I think maybe we'll have just 2 more questions. The gentleman in the pink shirt and the gentleman in the blue shirt. And maybe we can just get the questions and then perhaps a final answer. Okay. Would that be a good idea? Fine. So each can ask the question and then...
Hi, not a scientist, but interested in education. I was wondering, you were mentioning about Newtonian physics and teaching the stories of Newton as a way of kind of understanding and making sense of how we've come to conclusions about the world around us. And I was wondering if the history of science, perhaps one of its most important impacts on the world is in fact the way of studying the way that we have come to make sense of the natural world as a way of teaching the young people and introducing people to science as their kind of first way of being introduced to science by looking to the way that we have in the past tried to make sense of history. As you said, many of the things we've looked at the past, I mean, we may throw them out, we may laugh at them, but the same way they help us kind of understand the human condition, they may kind of help us understand how we can teach very complex, abstract phenomena. Mm-hmm. Does that make sense? As I mean, because I would argue that would possibly be one of the most important things for the history of science, in terms of being outside of just science as a field.
Yep. So maybe we just
take note, right.
Keep that, and then one last question.
It isn't actually really a question. I'd just like to say that I learned about Rumford's experiment on cannon barrels at school, boring cannon barrels with and blunter drills. It was 40 years before I actually came across an engraving showing his actual setup. Mm-hmm. And it would have made so many things much more clear. People tend to neglect things like that, the actual drawing, Uh-huh. And I think that's something that the history of science should do a lot more of.
Right, yes. Just briefly, as a rejoinder to that, yes, absolutely. I think sometimes visual material carries so much more power and stimulation than just the verbal stuff. And Rumford did publish those diagrams at the time, and they were not always transmitted, I guess, to people reading that stuff. The other question, I mean, that's the big one. In short, the answer is yes. I agree with you. I think the tracing of history in the way that you describe could play a very significant role in science education. And when I say science education, I mean both the education of people who are going to grow up to be scientists and the education of the other people who are just tortured with science. For what then? That's a huge question, but especially for the education of the people who aren't going to grow up to be professional scientists, I think this historical method is really the best way in which they can learn the methods and the nature of science. That was the spirit behind the famous general education program of James Bryant Conant at Harvard, just post-World War II program, which tried to teach science to the non-majors in a historical way. And Conant was a chemist, in fact, participated himself in the writing of the historical materials, which we can still look up and read. But I think that also connects slightly to the previous question. I mean, the question of method is really a very significant one, and one question we have to ask, which I'm not going to try to answer right now, is do scientific methods change and evolve as science progresses? And most philosophers would like to say, no, we want to find the eternal method, which will take care of us always. But I think looking at the details of history often belies that kind of simple idea about method. And that's another contribution that history can certainly make. So I'll stop there.
No, I think that's a wonderful stop, actually, because it enhances, again, your conclusion about the complementarity of history, philosophy of science, and science. So you can really contradict the scientists and says, that's what you think. But, we can have we can trace events and see how methods might indeed change that look to you unchangeable. But I do want to thank you very much, Professor Chang, for this extremely stimulating, beautifully presented lecture. You can see how many questions it did stimulate, and I have to say these were all very, very interesting questions and even more interesting answers, so we could go on and on. But we come to the most important part of the evening now, and that is me
yes, I forgot.
giving you the scroll for the lecture, for the award and a medal.
Thank you so much.
And even a check.
Thank you. Thank you.